Classical methods of analysis it includes copper assay, lead assay, zinc assay, iron assay. Copper assay determine the copper content in concentrates, ores, and materials essential in mining and metallurgy to assess resource quality and profitability. Various techniques, each with specific advantages and limitations, are chosen based on factors like accuracy, speed, and sample type. Overview of copper assaying methods: fire assay, electrogravimetric analysis, atomic absorption spectroscopy, X-ray fluorescence. First, fire assay, a classic method used primarily for determining precious metal like gold, silver, but also can be adapted for lead and other metals. Procedure: sample preparation: mix the ore sample with flux like lead oxide, soda ash, and a reducing agent like powdered charcoal. Fusion: place the mixture in a crucible and heat it in a furnace to high temperature around 1000 degrees Celsius. The lead collects the precious metals into a bead. Separation: weighing: after culling, separates the bead from the slag, clean it, and weigh it to determine the content of the precious metals. 2. Iodometric titration: a metric method to determine the concentration of cupric ions through a redox reaction involving iodine. Procedure: sample preparation: dissolve the lead containing sample in dilute sulfuric acid to convert lead to cupric ions. Reduction: add potassium iodide Ki to the solution, which reacts with Cu2 plus to release iodine. Titration: titrate the iodine with sodium thiosulfate until a pale yellow endpoint is reached using starch indicator to identify the endpoint where the solution turns from blue to colorless. 3. Electrogravimetric analysis: an electrochemical technique used to quantitatively determine the amount of metal deposited on an electrode. Procedure: sample preparation: dissolve the sample in a suitable electrolyte solution, sulfuric acid. Electrolysis: place an inert cathode in the solution and pass controlled current to deposit copper or lead onto the cathode. Weighing: after the electrolysis is complete, remove the cathode, dry it, and weigh it to find the mass of the deposit metal, allowing calculation of concentration. 4. Atomic absorption spectroscopy: a method for determining the concentration of metals by measuring the absorbance of light at specific wavelengths. Procedure: sample preparation: dissolve the metal containing sample in an appropriate acid solution. Calibration: prepare standard solution of unknown metal concentration of calibration. Measurement: introduce the sample solution into the AES instrument. The measuring instrument measures the absorbance of light at specific wavelengths for the target metal, allowing for concentration determination based on the calibration curve. Lead assay: methods determine the concentration of lead in ores, concentrates, and other materials, which is crucial. Evaluating lead-rich resources. Accurate assay results are essential for defining extraction techniques and ensuring quality control in the mining and metallurgical sectors. Overview of lead assaying methods: gravimetric analysis, atomic absorption spectroscopy, inductively coupled mass optical emission spectroscopy, X-ray fluorescence. First, gravimetric analysis. This method involves dissolving the zinc-containing sample and precipitating zinc as a compound for weighing. Procedure: dissolve the sample in dilute hydrochloric acid to convert zinc to zinc ions. Precipitate zinc by adding sodium phosphate to form zinc phosphate. Filter, dry, and weigh the precipitate to determine the zinc content. 2. Atomic absorption spectroscopy (AAS) measure the concentration of zinc by detecting the amount of light absorbed by zinc atoms in a sample solution. Procedure: dissolve the sample in an appropriate acid solution, often nitric acid. Prepare standard zinc solution for calibration. Use the AAS instrument to measure absorbance at a specific wavelength for zinc using the calibration curve to determine the concentration. 3. Inductively coupled plasma optical emission spectroscopy. This technique excites zinc atoms of plasma and measures the light emitted at characteristic wavelengths to quantify zinc concentration. Procedure: dissolve the sample in an acid, often hydrochloric or nitric acid. Introduce the sample solution into ICP's OES instrument. Measure the intensity of emitted light at the specific wavelengths for zinc to determine its concentration. X-ray fluorescence. This non-destructive technique uses X-ray to excite zinc atoms in a sample, causing them to emit fluorescent X-ray that are measured for quantification. Procedure: prepare the sample by grinding it to a fine powder for forming a pellet. Place the sample in the XRF analyzer Measure the emitted X-ray and use software to analyze the zinc concentration based on the intensity of the fluorescent signals. Zinc assay measures zinc concentration in ores and materials essential for assessing their quantity and economic value. Various methods exist which each with distinct advantage and limitation based on the current sample type. Overview of zinc assaying methods: gravimetric analysis, atomic absorption spectroscopy, inductively coupled plasma optical emission spectroscopy, X-ray fluorescence. Gravimetric analysis: this method involves the quantitative determination of zinc by precipitating it as a compound that can be weighed. Procedure: sample dissolution: dissolve the zinc containing sample in a dilute hydrochloric acid to convert zinc to zinc ions. Precipitation: add sodium phosphate to the solution which reacts with zinc to form zinc phosphate. Filtration and weighing: filter the precipitate, dry it in an oven and weigh it. Calculate the zinc content based on the mass of the precipitate. Atomic absorption spectroscopy: AAS measures the concentration of zinc in a sample by detecting the amount of light absorbed by zinc atoms. Procedure: sample preparation: dissolve the sample in appropriate acid solution, typically nitric acid, to create a clear solution. Calibration: prepare standard zinc solution of known concentration for calibration. Measurement: introduce the prepared sample solution into the AAS instrument. The instrument measures absorbance at a specific wavelength for zinc, allowing for concentration determination based on a calibration curve. 3. Inductively coupled plasma optical emission spectroscopy. This technique uses plasma to excite zinc atoms and measures the emitted light to quantify zinc concentration. Procedure: sample preparation: dissolve the sample in an acid solution, often hydrochloric or nitric acid. Sample introduction: introduce the solution into the ICP's OES instrument. Detection: measure the intensity of emitted light at specific wavelengths for zinc, allowing for the determination for its concentration based on standard curves. X-ray fluorescence: a non-destructive technique that uses X-ray to excite zinc atoms, causing them to emit fluorescence. Procedure: sample preparation: grind the sample to a fine powder or form a pellet. X-ray excitation: place the sample in the XRF analyzer and expose it to X-rays. Detection: measure the emitted fluorescent X-ray and analyze the intensity to quantify the zinc concentration using the instrument software. Iron assay is the process of determining the concentration of iron in various materials such as ores and metals. It is essential in industries like mining and metallurgy for evaluating the quality and economic value of iron-bearing materials. Overview of iron assay methods: gravimetric analysis, colorimetric analysis, atomic absorption spectroscopy, X-ray fluorescence. Gravimetric analysis: this classical method determines iron concentration by precipitating it as a compound that can be weighed. Procedure: sample preparation: dissolve the iron containing sample in hydrochloric acid to convert it iron into iron ions. Precipitation: add ammonium hydroxide to the solution to precipitate iron as iron hydroxide. Filtration and weighing: filter, wash, and dry the precipitate, then weigh it to calculate the iron content based on the mass of the precipitate. Colorimetric analysis: this method involves measuring color intensity of a solution to determine the concentration of iron. Procedure: sample preparation: dissolve the sample in an acid to obtain ions. Complex formation of the color reagents such as thiocyanate to form a colored complex with iron. Measurement: measure the absorbance of the color solution using a spectrophotometer at a specific wavelength to determine the concentration based on a standard curve. 3. Atomic absorption spectroscopy. AAS measures the concentration of iron in a sample by detecting the amount of light absorbed by iron atoms. Procedure: sample preparation: dissolve the iron containing sample in a suitable acid, often nitric acid, to prepare a clear solution. Calibration: prepare standard iron solution of known concentration for calibration. Measurement: introduce the sample into the AAS instrument. The instrument measures absorbance at a specific wavelength for iron, allowing for concentration determination based on a calibration curve. X-ray fluorescence: a non-destructive method that uses X-rays to excite iron atoms in a sample, causing them to emit fluorescent X-ray that can be measured. Procedure: sample preparation: grind the sample to a fine powder or form a pellet. X-ray excitation: place the sample in the XRF analyzer and expose it to a focused X-ray beam. Detection: measure the intensity of the emitted X-ray which corresponded to the iron concentration using the instrument app software. Instrumentation methods of analysis. It includes spectrophotometrics, ray diffraction, fluorescence, microanalysis. Spectrophotometry is the process of determining the concentration of iron in various materials such as ores and metals. It is essential in industries like mining and metallurgy for evaluating the quality and economic value of iron-bearing materials. Principle. According to the Beer-Lambert law, the amount of light observed is related to the concentration of the substance in the sample. Method. Prepare the sample in a solution. Set the spectrophotometer to the wavelength needed. Measure the light observance. Compare to the standard to find the concentration. Application. Measuring pollutants in water. Determining drug levels in medicine. Analyzing biological samples for various substances. X-ray diffraction fluorescence determines the structure of crystalline materials. Measure the elements present in the sample. Principle. XRD uses X-ray to see how they are scattered by crystal structures. XRF takes atoms in a sample with X-ray causing them to emit characteristic X-ray that reveal their elemental composition. XRD powder the samples, shine X-ray on it and record the diffraction pattern. XRF prepare the sample, expose it to X-rays and measure the emitted X-ray. Application. XRD identifying minerals and studying materials. Analyzing soil and metal for contaminants. Microanalysis, a technique to analyze very small sample or specific areas in materials. Principle. Uses electron microscope to analyze the emitted signals from a small sample, providing information about its composition. Method. Prepare a small sample, often very thin, place it in an electron microscope, analyze the emitted electrons or X-ray to determine the material's composition. Application. Studying metals and alloys, analyzing biological sample for research, investigating electronic components and devices. So that's all. Thank you.